Assalamualaikum and hi everyone. My name is Dr. Rohana binti Abdul Hamid. I am from Institute of Engineering Mathematics, Faculty of Applied and Human Sciences, Universiti Malaysia Perlis. Okay, today, I will present my research, which is Impulsively Started Shrinking Sheet of Dusty Flow, a Comparative Study. Okay, for introduction, this research involved boundary layer flow due to stretching or shrinking surface. This type of boundary layer flow have many applications such as in polymer industry, food manufacturing, process of hot rolling, metal coating, and many others. This boundary layer flow is introduced by Sakiadis in 1961. So impulsively started shrinking sheet means that for this problem, I consider unsteady flow, where the surface suddenly moves in stationary fluid. I also consider dusty fluid because it is possible that any foreign particles such as dust and other impurities to be present in the fluid. Result from many different production process. Let's move to literature review for this study. In 1961, Sakiadis studied stretching flow with constant velocity. Alright, and then followed by 1970, Crane studied the stretching flow with a linear wall velocity. And then in 1983, Banks studied stretching flow with power law wall velocity. And then in 1999, Macchiari and Keller studied stretching flow with exponential wall velocity. In the study of shrinking flow is it's the first studied by Miklavsis and Wang in 2006, where they said that shrinking flow will exist if we consider the fluid suction at the surface. So after the discovery by these researchers, then many researchers start to study about shrinking sheet flow. Such as in 2009, Fang et al. Studied the unsteady case for the shrinking flow. And then in 2020, Mahmoud et al. Revisited this problem by Fang using new formulation. Mahmoud et al. Claimed that the formulation by Miklavsin and Wang is not very accurate. So the objectives of this study is to compare the results from both formulation by Fang and also by Mahmoud, and then we include dust particles. We proceed to mathematical formulation. We consider an unsteady, incompressible, two-dimensional boundary layer flow due to permeable shrinking surface. So we consider fluid suction in this problem in stationary dusty fluid. And then the surface moves with velocity uw, and then the normal wall velocity is vw. So based on the boundary layer assumptions, based on the previous problem, the governing equations are, we have two phase. The first one is fluid phase, and then the second one is dust phase. So equation 1 is for the continuity equation for fluid phase, and the second one is for momentum equation for fluid phase. The third equation is for continuity equation dust phase, and for equation 4 is momentum equation for dust phase. And then we have initial and boundary conditions. Equation 5. Okay, so here we have UW. Where this is the surface velocity UW, which is the shrinking flow. Okay, in this problem we study shrinking flow, and then we have the boundary condition V. Okay, the normal velocity is VW. This is for fluid suction. Okay, so in Fang et al., after this I will consider as all formulation. Okay, use this similarity transformation 6. Okay, where okay, in the formulation by Fang, UW is defined as this equation. Okay, so using the previous similarity transformations, the governing equation 1 until 5 are transformed to equation 7 and 8. So we have this gamma here, the unsteadiness parameter, and then we have beta is the fluid dust interaction parameter, and L is the mass concentration parameter. Okay, with the boundary conditions, so F0 equal to S. S is the fluid suction. Okay, fluid suction, where S take the positive values. Okay, so this is the ordinary differential equations for if we use the old formulation by Fang et al. Okay, so using the new formulation as proposed by Hamid et al. In 2020, okay, they use this similarity transformation 10. Okay, so they claim that for unsteady flow, okay, will only exist if if the wall velocity follow this equation. So UW must follow this equation so that the flow exhibit self-similarity. Okay, they prove this equation by using group theoretic approach. Okay, so in this similarity transformation, they consider the nature of the problem, which is shrinking sheet. So UW here is the shrinking sheet. So negative here refer to the shrinking sheet flow. So using similarity transformation 10, the governing equations 1 until 5 are transformed to equation 11, 12, and also boundary conditions 13. Okay, you can see that we have similar, very similar equations with Fang et al. Earlier, but we have different sign here. Okay, while here for the new formulation, okay, the suction S takes negative value. Okay, so let's proceed to the results and discussion. Okay, this table 1, we compare the values of F double prime 0 with Hamid et al. Okay, you can see that the results agree well with the previous study. Okay, so for this figure 1, we plot the velocity profiles for different value of S. Okay, for different value of suction parameter. Okay, you can see that the profiles are like mirror image of each other. So from this figure also, you can see that the fluid suction reduce the boundary layer thickness. Okay, in table 2, okay, we plot the values of F double prime 0, okay, or wall shear stress for different L. L is the mass concentration. Okay, here you can see that, so using old formation or new formation, we get the same exact values, okay, but in different sign. Okay, same with table 3 if we plot values of f double prime 0 for different beta. Beta is the fluid dust interaction parameter. Okay, so using both formulation, we get the same values but in different sign. Okay, so figure 2 and also figure 3 is the velocity profiles for different L, okay, mass concentration. So, okay, this is figure 2 is for all formulation. Okay, you can see that the arrow here pointed, okay, up. Okay, but for a new formulation, we can see that the arrow is pointed down. Okay, we can say that when we increase the mass concentration, okay, the profile will reduce. Okay, for figure 4 and figure 5, we plot velocity profiles for different value of fluid dust interaction parameter. Okay, so we get the same, similar profile with the previous figures. Okay, so we can say that dust parameters, okay, dust parameters will reduce the fluid velocity. Okay, conclusion. For the conclusion, okay, unsteady dusty flow over a shrinking surface with fluid suction is investigated. Okay, we have considered two formulations of the shrinking flow. Okay, from the results, the profiles from both formulations are exactly mirror image of each other, and then and the profiles from the new formulation are similar with stretching flow. So that's all from me. Thank you very much.